Earth is an ancient world which has existed for more than 4.5 billion years. Just like the other planets in the solar system, which all formed around the same time as the Sun. But 4 billion years represents only a fraction of the universe's total life. And planets have almost certainly existed for longer. At the beginning of the universe, however, there were no planets. There was only hydrogen and helium gas, which went on to form stars, but not worlds. It was only later, when the universe's gas had evolved, that planetary systems started appearing out of the dust. Knowing when the first planets formed and what they were like is a complex question, with a broad range of considerations. But by studying the extrasolar planets of the Milky Way galaxy, we've learned that the Genesis planets may be older and more unfamiliar than we ever could have imagined. In order to know when the first planets began forming, we first need to understand how a planet forms. We have a pretty good idea of this, thanks to scores of successful missions to study the birth of new star systems. We know that stars and their accompanying planets begin as cold clouds of unassembled gas in space, containing many different elements and compounds, but primarily hydrogen and helium. The asymmetricity of these clouds means they are always fragmenting and interacting within themselves, contracting and eventually undergoing a gravitational collapse. This compresses matter from the cloud into a small, dense and hot seed, which will grow into a new star eventually, with the gas surrounding it collecting into an oven-like incubator which supplements the interior seed with more gas. Once the embryonic star reaches a certain mass, about 80 times that of Jupiter, it ignites a nuclear furnace and begins to shine, erupting powerful beams of energy which dispel the incubating cloud. This expelled gas then flattens into a spinning, scorching accretion disk around the star, which persists for around 10 million years. And it is at this stage in the young star's life that the race to form planets commences. All of the planets in a given star system form from material within the star's accretion disk during this 10 million year window, and once the disk has cleared, no new planets will ever be able to form around that star again. At the very start of this window, the disk will be extremely dense, and far too hot for anything to form inside. But as the young star erupts jets from its photosphere, some of this material is driven away, and the temperature within the disk falls to a level at which things begin to happen. Initially, particles condense to form tiny crystalline grains of dust, which are drawn to other grains to create clumps of material. Within a few 100,000 years, chunks of dust with diameters of a few centimeters will have formed, at which point they become massive enough to begin exerting an acute gravitational influence. This allows them to attract and accrete dust from their surrounding disk, increasing their mass and bringing them within range of other chunks. Within a million years or so, this process has given rise to rocks and boulders which exceed 1 kilometer in length, known as planetesimals. These chunks of rocky debris then barrel around their accretion disk, attracting dust and smashing into other boulders, building planetary cores from the ground up. The more massive a single object becomes, the better suited it is to gravitationally dominate its region of the disk, enabling the runaway accretion of much larger bodies at the expense of smaller ones. And thus, within only 100,000 years of the planetesimals taking shape, the majority of the system's planetary mass will be shared among a few dozen sub-Earth-sized rounded rocky cores known as planetary embryos. If these planetary embryos lie relatively close to their parent star, then collisions will determine their ultimate fate. Once the planetary formation window closes, these few dozen embryos will collide and merge into a handful of small rocky terrestrial planets, like Earth, Venus, Mars, and Mercury. Alternatively, if a budding planetary embryo lies much further away from the parent star, then it may lie in a region where it is cold enough to sustain another kind of planetesimal chunk, composed of frozen volatile substances like methane, ammonia, and water ice instead of rock. When cold enough to assume a solid form, these substances provide abundances of extra material for planetary formation. This can lead to the rapid accumulation of massive planetary cores, weighing more than 10 times the mass of the Earth. And if this happens early enough in the planetary formation window, then the icy core will attract stray hydrogen and helium atoms from the surrounding disk before they are blown away by the host star's ejections. These light elements collect in the planet's atmosphere until they form a thick, choking extended layer of critical point liquefied gas, known as a gas giant, like Saturn and Jupiter. These worlds can wind up being dozens of times the diameter of the Earth and hundreds of times more massive. However, not every icy planetary core that reaches this 10 Earth mass threshold will do so early enough to attract hydrogen and helium gas, as these elements will have already been largely dispersed. But the planetary core will still be able to attract a thick atmosphere of volatile ices, albeit not in as large quantities as a gas giant. And so we refer to this kind of planet as an ice giant, like Uranus and Neptune. Whatever forms during the planetary formation epoch, at the end of the window, the accretion disk will have cleared completely, having been accreted by planets or dispelled by radiation, and no new worlds will be able to form thereafter. And so, this provides a rather convenient means for astronomers to measure the age of an exoplanet. Because all natural satellites in a star system form with the primary, an accompanying planet will invariably be roughly the same age as its host, minus a few million years. And so, to know the age of an exoplanet, we simply need to know the age of the star it orbits. And to work that out, we need to know the star's metallicity. A star's metallicity is its share of elements heavier than hydrogen and helium. It's only ever a few percent at most, but this is still enough to drastically alter the chemistry and destiny of a star system. In astronomy, a metal is any element heavier than the two H's. So things like oxygen, carbon, nitrogen, and magnesium are all considered to be metals in this case. The planet-forming process we just discussed needs these metals. Without them, dust grains and planetesimal material would not be able to condense, and self-gravitating bodies would not arise. And there is only one place we know of where metals like this are synthesized: inside the cores of stars. Stars shine through the process of nuclear fusion, the crushing of light atomic nuclei to form heavier and more complex nuclei, or metals. When the first generation of stars illuminated the universe around 200 million years after it was born, there were no metals. Only hydrogen and helium gas left over from the Big Bang. Thus, these early stars were made almost entirely of primordial light elements, and lived very short and turbulent lives which ended in explosive supernovae. But during their brief energy-generating cycles, they are believed to have fused the universe's first metals, converting the fuel in their cores into elements like lithium, nitrogen, argon, and ultimately iron. Then, when these stars reached the end of their lives and exploded, these metals were ejected into their surrounding gas clouds, lacing interstellar mediums of hydrogen with heavy elements, each explosion contributing to the ever-evolving chemistry of the cosmos. And then the next time these gas clouds collapsed to form new stars, metals were mixed in with the process, ultimately enabling the formation of stabler, longer-living stars with higher metallicities. Therefore, we can derive a linear relationship between a star's metal content and its age. The higher a star's metallicity, the later it must have formed, with a higher number of gas-enriching supernovae preceding it. Thus, it is a young star. Alternatively, metal-poor stars, which show a distinct lack of heavy elements, must have emerged at a time when the universe's gas was not nearly as enriched as it is today, and thus the star is probably ancient. As mentioned, metallicity would have been close to zero within the oldest generations of stars, and planetary systems wouldn't have been able to form that early on. But it seems at some point, the universe crossed a threshold at which its stars were enriched with enough metal to start grinding out planets through accretion. And so, the key to knowing when those first planets took shape lies in understanding when the cosmos was enriched to the level sufficient. In order to get a better idea of when this might have happened, scientists spent decades scouring the Milky Way galaxy to find its oldest stars and worlds. Back then, we had two main ways of identifying exoplanets, either by spotting them as they pass in front of their parent star and transit the light source relative to the Earth, or by spotting the wobbles in a star's spectrum as a result of a companion object acting on it. Both methods, however, are prone to biases, which impeded our early perceptions of the Milky Way's planetary population. Both means favour the detection of very large Jupiter-sized worlds orbiting close to their parent stars. This type of planet is known as a hot Jupiter. They are gas giants which have migrated inwards through their system as they have accreted material, winding up very close to the parent star indeed, where they exert the most detectable wobble and transit most regularly, improving our chances of picking one up. As such, it was hot Jupiters that revealed themselves to us most frequently in our earliest, least sensitive exoplanetary surveys in the mid-1990s, leading us to conclude that they were the prevailing type of world beyond the solar system and a good indicator of the types of stars that can support planets. The thing is that hot Jupiters prefer higher metallicity star systems with large amounts of dust. In order to get this big, a gas giant needs to accrete vast amounts of rocky and volatile material, which there simply wouldn't have been enough of in early metal-poor star systems. Thus, we only really find core accretion gas giants like Jupiter in systems with high metallicities. And because they accounted for the majority of known exoplanets back then, This led us to incorrectly conclude that planetary systems need sun-like levels of metallicity to exist, and that space subsequently wouldn't have been enriched to the level sufficient until about 6 or 7 billion years after the Big Bang, just under half the universe's present age. That is a long time without any planets, and it would have damning implications on the probability of alien life elsewhere in the cosmos. But moving into the 21st century, we began to realise that this wasn't the case. Thanks to technologically superior observatories like Hubble, Spitzer and Kepler, transit surveys and wobble detections became the work of computers, capable of tracking thousands of stars at once to identify even the most discrete signs of satellites. Today, we've identified over 5,000 exoplanets, in an array of different sizes and types, with some boasting ages of more than 10 billion years. And among the oldest and most jaw-dropping of these worlds is the hellish planet Methuselah. Methuselah is, to date, the oldest planet we've ever discovered. Appropriately named after a biblical patriarch who was claimed in the book of Genesis to have lived for just under 1,000 years. His namesake planet lies around 7,200 light-years away from Earth, in the constellation of Scorpius, near the heart of the ancient globular star cluster Messier 4. For a long time, it was thought that the stars within globular clusters would not be capable of hosting planetary systems. The lack of metals, the contrasting tidal gravitational influences, and strong stellar wind emissions produced by these tightly packed stars was expected to dispel protoplanetary disks before they had a chance to condense, rendering planetary formation impossible. As such, we never thought we would find a planet inside one of these old, inhospitable star clusters, and our early observations of globular clusters seemed to back this up, when we failed to detect any evidence of hot Jupiters lying within. But in M4, the story is different. In 2003, the Hubble telescope identified several metal-poor helium white dwarf stars, with estimated ages of around 13 billion years, making them among the very oldest stars we've ever discovered. And loosely bound to one of them, in spite of the harsh stellar neighbourhood, is the planet Methuselah. Its discovery represented a number of record-breaking firsts in the field of planetary science. In addition to being the oldest planet we've ever found, it was also the farthest that had been discovered at the time, and the first inside a globular cluster. And it was even the first circumbinary exoplanet ever discovered, orbiting not one but two burned out post-main sequence stars near the core of the cluster. One of Methuselah's binary hosts is the aforementioned ancient white dwarf, the exposed core of a dead star too small to go supernova. The other component is a neutron star, the core of a dead star that was large enough to go supernova, leaving behind an ultra-compressed, irradiating, city-sized sphere of neutron-degenerate matter. And it was through this object that we were able to discover Methuselah. PSR B16 2026 is a pulsar, meaning the neutron star emits beams of radiation from its polar axes as it rotates, which periodically fall in the direction of Earth, where they are detectable as a series of precisely timed, lighthouse-like pulses. This allowed us to identify the system in 1988, and in the years since we have managed to identify gravitational companions thanks to the wobbles they cause in the pulsar's spectrum. Almost straight away, astronomers inferred the presence of a second body in the system thanks to the obvious effect it had on the signal. But throughout the 1990s, the possibility of a third body, orbiting well beyond the binary barycenter, was also debated, thought to be either a low-mass star or perhaps a particularly massive planet. By 2003, the latter hypothesis was all but confirmed, when NASA used Hubble to identify the white dwarf in the system, and from that deduce an accompanying planetary mass body, around 2.5 times more massive than Jupiter. That body is the planet Methuselah, an ancient visitor to this most torrid of star systems, orbiting well adrift of the chaos at a distance of 23 astronomical units. Given the planet's wide orbit and hostile neighbourhood, it is improbable that Methuselah is a true satellite of this system. Rather, it is thought that the planet formed further out in M4, around a solitary star with a dusty disk, before gravitational disturbances knocked it out of its neighbourhood and sent it hurtling towards the core of the cluster. Then it became entangled in the grip of this colossal tug-of-war between ghost stars, where it remains orbiting to this day, completing a full lap of the system once every century. However, assuming the planet formed somewhere within M4, then it is probably around the same age as the rest of the cluster, whose 100,000 constituent stars were born together rapidly in the early universe. This gives Methuselah a truly staggering estimated age of some 12.7 billion years, little under 3 times the age of Earth, completely uprooting our long-held perception that planets need metal-rich stars to exist. The most intriguing thing about this planet's existence is that it is a gas giant. And not just any gas giant, one more than 2.5 times the mass of Jupiter. Even if we had expected to see planets in such ancient, low metallicity star systems, we would have expected very small, immature rocky worlds, ground out from the scraps of metallic gas that would have been available at the time. Yet Methuselah not only managed to form in this most simplistic of chemistries, but somehow managed to accrue more mass than the entirety of the solar system's planets. At this early stage in the universe's life, Methuselah certainly wouldn't have reached this size via core accretion, the process we discussed at the beginning, where rocky planetary embryos reach 10 Earth masses and attract a gaseous atmosphere. That process requires a substantial quantity of metals, the likes of which there just wouldn't have been in this ancient globular cluster. And so, this suggests that Methuselah may have formed via another planetary formation mechanism, one which relies far less on metals and thus has enabled their existence throughout the duration of the universe's life. We now believe that, in the very oldest star systems, born with high fractions of hydrogen and helium gas, planetesimal coagulation may not have been necessary to form giant planets. Instead, gravitational instabilities within these dense primordial disks would have resulted in the contraction of clumps of light gas into self-gravitating bodies. If one such clump became sufficiently massive and compact, then dust grains would have condensed inside the object, from the trace quantities of metal elements present in the planet-forming disk. These dust grains would have then sunk towards the centre of the body and formed a makeshift planetary core, allowing the clump to begin acting as its own planet. This new world would have then swept round its young stellar disk, clearing vast trails in the system's hydrogen and helium gas, forming a massive, dense atmosphere and ultimately becoming its own type of heavy-duty gas giant made mostly of light elements. Therefore, even in the absence of essential core-accreting materials, gas giants like Methuselah, which formed in this manner, would have been able to dominate their planetary systems to attain super-Jupiter sizes, even in the most metal-poor environments. This type of gas giant may well have been incredibly rare in the early universe, as the prevalence of gas giants is exponentially tied to rates of metallicity. But the existence of Methuselah alone shows us that the formation of planets was clearly underway within only 1 billion years of the Big Bang. And so, if gas giants have been able to form for the longest time, then what about terrestrial planets? When did the first landscapes appear to overlook the young universe? As we mentioned, the process of rocky core accretion builds from the ground up, and so hypothetically, this should have enabled the formation of small terrestrial planets long before it could give rise to larger ones. These planets would have required at least some level of metals, and so may have taken a bit longer to emerge than primordial gas giants like Methuselah. But even so, it does seem like terrestrials have been forming, in this galaxy at least, for well over 10 billion years, with their existence seeming to be much more indiscriminate when it comes to metallicity. We've uncovered hundreds of these rocky exoplanets in the Milky Way, around stars of varying ages. Among the oldest are those worlds residing in the Kepler 444 system, an ancient triple star system lying 119 light-years away from the Earth. The system's primary body is a low-mass orange dwarf star, which is home to no less than 5 terrestrial exoplanets. They range in sizes from Mercury to Venus, and all have settled, stable orbits, implying that there are no gas giants on the inner part of the system. Unfortunately, none of these rocky worlds are thought to be habitable. They all orbit closer to their parent star than Mercury to the Sun, rendering their surfaces scorched and lifeless. But with an estimated age of more than 11.2 billion years, these worlds show us that the framework for rocky terrestrial planets has been in place for almost as long as that of gas giants, and that both types of world have been able to form throughout the majority of the universe's life, their emergence far less reliant on metals than we once realised. With all these things considered, we can conclude that the planetary formation mechanism, whichever form it may take, is robust and resilient, able to manifest in a wide variety of circumstances, even in the absence of high metallicities. As such, planets are very likely to be abundant throughout the universe, with each galaxy housing hundreds of billions of every possible type and age. And so, the inevitable follow-on question is, if terrestrial planets have existed for most of cosmic time, then how soon after their emergence did they become capable of supporting life? If the universe's terrestrial worlds have had more than 10 billion years to find balance, then it fundamentally increases the probability of other sources of life elsewhere in space. But of course, habitable worlds require a much more precise and refined set of circumstances than your average lifeless terrestrial. To make a rocky world livable, you need all sorts of complex ingredients: temperate atmospheres, chemical compounds, energy gradients, and above all, a flowing liquid solvent, for mixing molecules and facilitating life-giving chemical reactions. On Earth, that solvent is water, which has flowed in a liquid form on the planet's surface for billions of years. However, there are a number of other substances, such as ammonia, which possess the hydrogen bonding properties necessary for biochemistry when in a liquid form. And thus we can envision a wide variety of chemical recipes for the emergence of life. The key thing that all these recipes need, however, is time. Balanced, temperate conditions need to remain largely undisturbed for hundreds of millions of years, or perhaps even longer, to allow enough time for the unknowably complex chain reactions of abiogenesis to proceed. This effectively rules out the universe's first populations of stars from discussions surrounding habitability. In addition to lacking sufficient quantities of chemical compounds, these early stars would have not lived anywhere near long enough to sustain the formation of planetary systems. Galaxies would have also been flooded with stellar wind, supernova shockwaves, and cosmic rays, strong enough to snuff out any budding biosphere. But once the stubbornly high star formation rates that characterized the early universe had died down, galaxies would have almost certainly started to bear habitable rocky planets after a few billion years. Whether any of these worlds ultimately resulted in habitation depends on the number of opportunities there have been for life to emerge. For a long time, astronomers believed that the galactic habitable zone, the postulated belt of the Milky Way with the right balance of stability and metallicity to enable habitability, would make up only a very small part of its total expanse. Galaxies like the Milky Way tend to evolve chemically from the inside out, with the majority of metal-infusing supernovae occurring within the crowded galactic core, resulting in centralized higher metallicities. In contrast, further away from the galactic nucleus, stars become more spread out, and subsequently lie in the paths of fewer supernovae, constraining their access to metals. Therefore, it was once believed that the outskirts of the Milky Way and all spiral galaxies would be badlands, almost entirely devoid of planets altogether, let alone habitable ones. This considerably reduced our estimate of the number of potential opportunities for life, by excluding hundreds of billions of potential star systems from consideration. But in recent years, we've seen evidence that planets were indeed forming in metal-poor environments. The question is, how did such large areas of the galaxy come to be enriched to the level needed for planetary systems so early on? Scientists have probed the depths of the universe in an attempt to determine the metallicity of the oldest galaxies, by using the background light of quasars as an illuminator for taking spectral measurements. What they found was that sun-like levels of metallicity could be found in galaxies all the way out to redshift 10, little under 13 billion years ago. Finding metals inside these oldest galaxies isn't wholly surprising on its own. After all, star formation rates would have been at their highest during this era, resulting in vastly enhanced rates of metal-generating supernovae. But this early on in the evolution of the cosmos, barely a billion years after it was born, you would expect the scarce number of newly synthesized metals to occupy only a relatively small region near the crowded galactic core, where the bulk of stellar enrichment would have been occurring. But instead, scientists were stunned to find traces of metals in primordial galaxies as far out as 50,000 light-years from their respective galaxy cores. Even this early in the universe's life, the few metals that had been produced were still finding their way across the entire expanse of their host galaxies. The most probable reason for this breakneck spread is the radiation from a starburst event, which gave freshly created metals in the heart of the galaxy a lift into the outer rims. Back then, bustling colonies of newly formed stars would have emitted so much stellar radiation that any metals released by supernovae would have been forced outwards by radiation pressure, pushing them as far out as to seed even the more remote metal poor star systems with new heavy elements. At the time, the high volumes of stellar radiation would have rendered these young galaxies uninhabitable. But once the starburst events ended, they left behind enormous swathes of enriched gas all over their host galaxies. This could have resulted in an explosion of worlds with habitable properties throughout galaxies right across the universe, just as soon as the conditions became right for their emergence. And with the groundwork for livable planets laid across such vast areas so early on, it makes it ever the more likely that one of these worlds would have clicked into an awakening of life independent of our own. Unfortunately, until we find solid, indisputable evidence of that somewhere else in space, we can never say for certain that any quantity of habitable worlds is enough. Even if the galaxy is brimming with temperate water worlds and Earth analogues, life may be so complex that even the estimated 100 billion planets of the Milky Way galaxy are not sufficient for more than one inhabited world. But in any case, and even if the galaxy is completely lifeless besides Earth, the sheer number of rich, complex and temperate worlds that have managed to emerge out of the chaos of the early cosmos, it's nothing short of a miracle. Just think of the fascinating stories that may have played out on some of these worlds over 12 billion years.